Welcome back. Now we're going to learn about functional blocks of logic gates. So we're going to put together a configuration of logic gates that do a specified function for us. And we're going to learn about two specific ones today, a multiplexer and a decoder. And then we'll talk about chips that they make that can be programmed to do any possible logic you want because they have a configuration of gates in them. And those are called PLAs, or programmable logic arrays. Okay, so let us start with the multiplexer. You can think of the multiplexer as a selector. So we have S here, which selects which of the inputs we're going to output over here at F. So if S is 0, we'll output whatever W0 is, or W0. And so if that W0 is 0, then we'll output a 0. If it's a 1, we'll output a 1. And then similarly, if the selector is set to 1, it means we'll look at this input right here and we'll output whatever W1 is, whether that's a 0 or a 1. Similarly, we could have 4 inputs that we're multiplexing. And so then we'll have to have 2 selector inputs because we need 2 bits, right, to represent 4 possibilities. And so then if the selectors are 0, 0, right, it'll tell us to look at this input wire. 0, 1, this input wire. 1, 0, we'll look at this wire, or 1, 1, we'll look at whatever the input value is on that wire. And then each of those can be a 0 or 1. So W0, W1, W2, W3 here. And so these are useful in computer systems because you may be sending data around. And as you send around data, you may be wanting to say, hey, like, I want to choose whatever data is coming in on this channel. And so that's kind of what a multiplexer does for you. Now, how is a multiplexer actually made? Well, here's what the actual circuit would look like under the hood. So let us take a look at the 2-to-1 example. Let's try to see how that creates the multiplexer we want. Well, if we try to create a logic expression for these gates over here, we'll see that we have W0 and not S for this right here. And down here, we have S and W1. The product there for you. And then they get ORed together in this final step right here. Okay, now let's compare that to the truth table we had on the other page, right? We had that S had to be 0, so that's not S over here. And then in that case, we output whatever W0 is. So W0, if it's 0, right, that means we're outputting a 0. And if W1 not was a 1, then not S, since S is 0, not S is 1. So then I have 1 and 1, so I will output a 1. So essentially, I output whatever of W0 is in that case. And then similarly, if I have a 1, then this whole half is going to become a 0 and something else. But if it's 0, then no matter what the other thing in the expression is, we can't output anything here. So that's why we're going to kind of ignore that one now. And now we have the S is 1 over here. And similarly, when S was 0, this was going to be 0. So no matter what this was going to output a 0 for us. Okay, so now in this case, we have S is 1 here. And then if W1 is 0, 1 and 0 is going to give a 0. So we get what W1 was, which was 0. And if W1 is 1, then we have 1 and 1. So indeed, we output a 1. And in the end, we get out a 1. And because we're ORing that with a 0, it doesn't really matter that the other one's 0. Okay. I'm not necessarily going to work through the whole details of this circuit, but I think what is important here to notice is kind of an order coming about. Notice that they first have NOT gates, then they have AND gates, and then finally they have OR gates here. And the reason they do that is because of the way we've been formulating our Boolean expressions. In the last video, we learned about product of sums, right? Where we looked at each row of the table where the output should be 1, and then we ANDed things accordingly for that row. And then for every row that was 1, we ORed that to a different row, right? For example. And so notice that in this formulation, first we NOT things, then we AND them, and then finally we OR them. So the fact that we're formulating our Boolean expressions using that algorithm means we always end up with a generic thing that can be NOTs and then ANDs and then finally ORs in that order. Okay, now let us talk about the decoder. I kind of like to think of the decoder as the opposite of the multiplexer. Specifically, it's, I guess I should say, a binary decoder is somewhat the opposite of a multiplexer, as you can have other kinds of decoders too. So in that case, we're going to have an input over here, which is a binary number, and then it's going to tell us which output to turn on over here. And why I say this is a binary decoder, right, is I could use some other kind of code, right? These zeros or ones could be some secret code that you and I have to talk to each other. It doesn't actually have to be binary numbers. Okay, so let's take a look at this. If I input a 0, 0, that means I want to output a 1 on the first output wire. If I input a 1 and a 0, because notice, I guess one important thing to notice is which of these is the most significant digit or the least significant digit. So normally W1 refers to the most significant bit, and this is the least significant bit. So in that case, when I input 1, 0 over here like this, that's technically this row of the table. And so then my Y1 here is going to have an output of 1. And so on and so forth. If I do the next number in binary, I'll get an output of 1 on the next output wire. And then if I put in 1, 1, I'll get an output of 1 on the final output wire. So essentially, I'm selecting which wire at the output I'm going to output a 1 on, and everything else is going to be 0 in that case. So at any time, there's only one output that's high. Okay, let's take a peek at the circuit that will implement this. So for Y0, right, we got to look at each output individually. And so Y0, what does that look like to you? It's only a 1 when both W1 and W0 are 0. So that's why we send in right here, not W0, not W1. And then AND those together, and that's the only case for which we want Y0 to be 1 or high. Similarly, Y1, the only time we want the output to be 1 is when W1 is 0. So W1 is 0. So that's not W1. And W0 is 1. So W0, tracing down this way, is true. And then similarly for Y2, it'll be when we have W1 and not W0. And then for Y3, so this is for Y2, and then Y3 will be when W1 and W0 are both true, or both 1. So we're sending down W1 and W0. Okay. So we've just seen two different circuits here, right, where we're doing these nots, and then we're doing these ands, and then finally there were some ors on the last one, on the multiplexer, but there weren't any ors in this case. So we're following that same order, and we talked about how that matched the way we're formulating the Boolean expressions by rows of the table that output 1. And so we can just generalize this and create a grid of a bunch of NOT gates and OR gates and OR gates. And then we can program connections to connect to those gates as desired and create any logic network we want. And that is called a programmable logic array. And so you can think of it kind of as a black box. It has a bunch of inputs that give outputs, and you could create a truth table for that, and you can program it to output any truth table you want. Okay, so this is kind of what it looks like on the inside. First, we put a bunch of inverters so that you have both like X1 and it's not, the not X1 sitting available. Then we have what's called the AND plane, where all the AND gates are. And then finally, we have the OR plane over here as the last thing before the output. And then if we blow up even more, we can see this is the AND plane here in this red box, and this is the OR plane. And we have wires connecting. And then these right here represent programmable connections. So I can go program a connection here if I want, for example, where I just drew this line here, if I want X3 involved in this AND, then I can connect a wire there. Or if I'd rather have not X3 involved, right, then I'm not going to connect a wire there, and I'm going to connect a wire down here for the not X3. So that's connected to not X3. So it may be big, it may be clunky looking, but it's nice that you can program this thing to do any possible output combination you want. So any truth table can be implemented. And then they also have something called a PAL device, programmable array logic. I know that's confusing because the other one is PLA. And so this one has programmable ANDs, but fixed ORs. And that makes it a little easier to manufacture and cheaper. So that is a common trip also that exists that you could program. And again, they draw these little X's here to show wherever they programmed a connection. Okay. And then finally, there are other types of programmable logic devices out there. So the whole class of programmable logic devices is called PLDs instead of PLAs. And so we have things like complex programmable logic devices or field programmable gate arrays. And field programmable gate arrays, FPGAs, that is something you will play with later if you take 3700 and follow on courses from there in the computer engineering track. You will learn how to program those and operate them and test them. So let's take a little peek at what a field programmable field programmable gate array looks like under the cover. So it's a programmable integrated circuit and has these fixed logic blocks. So you can see here that a lot of the stuff here, right, all this red stuff is actually interconnection switches. And then you've got these logic blocks sitting in between. And then wires on the outside here where you can connect your inputs and your outputs. And so these interconnect switches, these are the configurable connections, and FPGAs are often used in research and development so that you can basically test a circuit out and see if this really works for your industrial application. And if it does, then maybe you'll go and print an actual chip that does that. But it's really expensive to get a chip designed and made. And so you want to test it all first on one of these field programmable gate array systems. So a single device has thousands of these switches. So you don't want to be thinking necessarily about every single switch and whether it's going to be on or off. And so that's why we have computer systems to aid in the design of this. So computer aided design stands for CAD. So maybe you've heard the word CAD in the context of usually people have heard of it in mechanical engineering kind of sense, like SolidWorks, where you lay out a 3D design and then you can 3D print it, for example. But CAD exists in other realms, right? It exists for computer engineers, as I'm talking about right now for these programmable logic devices. It also exists in the optics world to lay out lenses, for example, which is something I'm familiar with. So we call this hardware design language, is what they use to program all these programmable switches. And an example of a hardware design language is Verilog, which is what you learn in 3700, and I believe you continue using in 3710. And so the program then, you can give it logic expressions and it will actually figure out which switches should be on or off to implement that logic expression you give it. So it's a pretty powerful tool, and there are a number of ways you can program it, and the nitty-gritty of all that will be yours to explore in 3700. And then the final application I want to talk about here is ROM, or read-only memory, because it also involves some kind of programmable type switches and decoders and gate arrays, similar to all these things we've been talking about. So when you store something in memory, your computer CPU has to be like, oh, I need the data stored at this address. So it sends off and it says, I'm looking for something at this address. So here's the address being put in. And then that address, right, because of a decoder, is going to point to a specific line coming out of here, right? One of these 64 different outputs. And so it'll output a 1 just onto, for example, if we called this spot, right, then that means we output a 1 here for all of these. And so that way we've called a unique place in the memory, and we can look at the stored number that comes out. And we stored the number by connecting these fuses here when we created the memory. Again, I am totally oversimplifying this, and I'm doing this just to give you a sliver of why do I care? Why should I learn this? And if this stuff interests you, you should definitely go on to more courses in computer engineering. And with that, I will see you on the next lecture video.